on to confidence intervals in the linear regression model setting. The setup is precisely the same as the one for hypothesis testing. So we have a linear regression model, we have random sampling, and we have Gauss-Markov. One explanatory variable, and we have this additional assumption that the error term actually follows a normal distribution. But we'll see, just like in the lecture when we talked about hypothesis testing, this assumption is not so crucial. It will actually work pretty well even if the errors are not normal, as long as n is not too small. So confidence intervals for an unknown parameter such as beta 2 is an interval, and we hope that this interval will actually contain the true parameter beta 2. In fact, we design the interval such that there is a pre-specified probability of this happening. The common probability to use is 95%. So a 95% confidence interval is an interval that contains the true parameter with a 95% probability. So more formally, for any level of significance alpha, then we define the 1 minus alpha times 100% confidence interval for beta as follows. Note that the common value for alpha, 5% or 0.05, will give us 1 minus alpha to be 0.95, multiply that by 100, so it would say 95% confidence interval. Correspondingly, a level of significance of 1% would correspond to a 99% confidence interval. The interval is formed with B2 at the center. To B2 we add plus minus the critical value times the standard error of B2. And it can be shown that this interval will contain beta 2 with a 95% probability if alpha is 5%, and correspondingly for other values of alpha. So we can actually show this. The probability that beta 2 is inside this 95% confidence interval, or whatever alpha is precisely 1 minus alpha times 100%. Just like for hypothesis testing, for this to be exactly true, the error terms must be normally distributed. And if they're not, if the Gauss-Markov assumptions are satisfied, but the errors follow another distribution, not normal, then as long as n is large, this interval will be approximately correct. Typically, if n is larger than, say, 30, the difference between the confidence calculated by this formula and the correct confidence interval is typically minor. So let's see this in action, how we can calculate confidence intervals. Here we have the same simulation that we considered for hypothesis testing. I am drawing the error terms from a normal distribution, and the exogeneity we can see here from the 0, and the homoscedastic errors we can see here that all the variances are the same. I have here the B2, and here is the standard error of B2. So let's pick an arbitrary alpha such as 5%. So we will construct a 95% confidence interval. Then this is the critical value. So we are ready to calculate the confidence interval. So the left-hand limit of the confidence interval is then the estimated B2, let's type that, equal to this number here minus, because we're doing the left-hand side, the critical t-value multiplied by the standard error. So that would be the left-hand limit. The right-hand limit would be almost the same except for with a plus sign. So it will be equal to B2 plus the critical value times the standard error. So this is the interval between 1.77 and 2.22. That's the confidence interval. Remember, the true beta 2 in this case is 2, so this time we did catch the true value inside the confidence interval. So what should happen now if I F9 this experiment is that I will get beta 2 inside the interval in 95% of the cases. That is in 1 out of 20 simulations. So do it again. Got it. Inside, inside, inside. Here we failed. Here it's actually outside the confidence interval. And that will happen in 1 out of 20 cases. So you do have this 5% probability of giving a confidence interval that actually doesn't contain the true parameter. So there are a couple of things that you should notice with this confidence interval. And first of all, the width. The interval is always centered at B2. It's centered at the OLS estimate. The plus minus term, the term after the plus minus sign, will determine the width of the interval. So you can see, for example, that a high standard error will correspond to a wide confidence interval. If you think about that, that makes sense. The standard error is a measure of how well we are able to estimate beta 2. If standard error is large, we do a pretty poor job in estimation, and we should correspondingly have a pretty wide confidence interval to reflect our uncertainty. You can also see that it depends on this critical value. The critical value decreases with n. That too makes sense. That should make the confidence interval smaller. Also remember, if you make alpha smaller, make the tail smaller, that will increase the critical value, and that will increase the width of the confidence interval. That too makes sense. If you start with a 95% confidence interval corresponding to alpha 5%, and you go and you want to consider a 99% confidence interval, alpha equal to 0.01, then you must use a much larger critical value and you will get a much wider confidence interval. If you think about that, that makes sense. If you want to be 99% sure that you capture the true beta, you need to provide a wider confidence interval. So that's the trade-off. I mean, we want alpha to be small. We would like to have a confidence interval preferably at 100%. But as you take alpha down to 0, you also take the critical value to infinity. So the only way you can get a confidence interval of 100% is to say that the beta is somewhere between plus minus infinity. So there's a trade-off between precision in terms of a low alpha and usefulness in terms of a confidence interval which is not too wide. If you use the Excel add-in, the data analysis and the regression tool as described in the hypothesis lecture, you can get more statistics even in Excel. So then you would actually get the 95% confidence interval of both beta 1 and beta 2. So this would be the 95% confidence interval of beta 2. Again, you can just double check this number here in cell F18 is just the coefficient minus this one, standard error, times the critical value, which is not printed in this output, but which you can find easily, and the upper one similarly with the plus sign. There is actually another thing that you can notice from this example, and that's the following. In this example, we do not reject the null that beta 2 is 0 at 5%. The p-value is much lower than 5%. Sorry, I think I said we do not reject. I of course mean that we do reject the null that the beta 2 is 0 at the 5% level. This coefficient b2 is significantly larger than 0. Well, if that's the case, if we have rejected the possibility that b2 is 0, then 0 will not be included in the confidence interval. And you can see that the confidence interval goes from 0.03 about to 0.08. And this will always be true. If you reject the null that beta 2 is equal to 0, then 0 will not be in the confidence interval, and vice versa. If you cannot reject that beta 2 is 0, then 0 will be in the confidence interval. To get confidence intervals in Gretel, you do your regression first of all. So let's see, we go to model ordinary squares. The model I'm considering right now is explaining final with SATM, like that. Gretel doesn't immediately plot the confidence intervals, but you can get the 95% one from going to the analysis, confidence interval for coefficients. You get 95% confidence interval for beta 2, 0.028 to 0.0828 something, just like we got in Excel. You can get other confidence interval than just the 95% if you just click on the alpha, which is the level of significance, and pick a value for 1 minus alpha. So if you want the 99% confidence interval corresponding to alpha 0.01, then you get something which is wider. In eViews, we need to estimate the equation. So quick estimate equation. We do final C and SATM like this, and then same as for Gretel, it doesn't print the confidence interval in the printout, but you can easily get them by going to View, Confidence Diagnostics, Confidence Intervals, and you can type whatever you want here. And like this, you can do several values. So if you do 0.9, 0.95, and 0.99, you actually get 3 sets of confidence intervals for each beta parameter. So we can see then that the first one would be the 90%. Here's the 95 one for beta 2, the left hand and the right hand, same as the other software. You can also get the confidence interval for the intercept, and I haven't provided you with the formula, and that's because it's exactly the same. So the confidence interval for beta 1 would be B1 plus minus the critical value times the standard error for B1.